We'll go ahead and get started. Yeah, so two relatively easy lessons today. The first section is just going to have you approximate areas using rectangles. It's going to give you some function that you're going to know what the function is. So this could have been something like f of x is equal to, let's see what would make sense here, maybe something like x minus 2 squared plus 4. Just a parabola shifted 2 units to the right and up 4, some upside down area. And the first section is simply going to have you approximate the area using rectangles. And it's going to tell you some different rectangles to use. So one way that we can approximate this area, the author might tell you something like, split it up into 8 even rectangles and use something called an upper sum. So when I split this up into 8 rectangles, it's pretty 8 even rectangles, it's pretty obvious what my bases are going to look like. The only question is, how high up should I make my rectangle go? How big should the rectangle right here be that I use to approximate the area here? And so there's a bunch of different ways that the author is going to have you do it. When he says use the upper sum, he means use the highest point. So drawing in blue here now how we would do our rectangles. If we do an upper sum, this rectangle would use the highest point on that interval. This rectangle would use the highest point on that interval. This would use the highest point on that interval, highest point on that interval, and your rectangles would look something like that. And you approximate the area exactly how you would know. You calculate the height of the function at that point and multiply it by that width, and that gives you that area. And it's kind of a tedious process. I remember the first time I went through this, I kind of felt like a waste of time. Why is the author making us do this? And he's trying to prime your intuition for what's coming, which is integrals. Which integrals are going to be arbitrarily good approximations of area. The same way that when you remember back when we were talking about derivative, and I said I have some function, and what's the slope of the function at this point? What did we do? We started by picking some other point, calculate the slope between those 2 points, and then we pick a point even closer and closer and closer, and as the next point we use gets closer and closer to this point, our slope gets better and better. Same thing is going to happen here. So the author is going to have you calculate the areas using a bunch of rectangles. These rectangles we're using what we call an upper sum. He might have told you to use a lower sum, which is use the lowest point to get the rectangle. So this rectangle wouldn't have a height. The height of this rectangle would be that. The height of this rectangle would be that. The height of this rectangle would be that, and then this rectangle wouldn't have a height. There's another way we could have done it. Now these are stupid approximations, the same way that when I was trying to approximate the slope here, and I use these 2 points, I get a stupid approximation of the slope. The author's just giving you the idea of what an integral is going to be. So he might tell you to use lower sums, he might tell you to use upper sums, he might tell you to use the midpoint. Use the height of the rectangle at the midpoint. So at the middle of this width is right here, so maybe use this rectangle as our height. And then for this one, take its midpoint, which is about right there, and use this rectangle to approximate the area there, and etc. And he might tell you to use the left-hand point of each rectangle, and he might tell you to use the right-hand point of each rectangle. The point is going to be, if we use infinitely many rectangles, we keep breaking our rectangles down smaller and smaller and smaller, it doesn't really matter which of those points you use. You're going to get an arbitrarily good approximation for the area. So that's what the first section is going to be about. It's just approximating areas using rectangles. Pretty straightforward. The second section is just about this sigma notation and how to read the sigma notation and make calculations using sigma notation. That's the first 2 sections. Section 5.3 is the big one in this chapter. We won't be covering it until next week, but I'm going to try and motivate it largely today. This is the one that now gives you the definition of an integral. I told you, what are the 4 big ideas of calculus?
Derivatives, integrals.
Limits, continuity, derivatives, integrals. We've covered the first 3. All that's left now is integrals.
Yeah.
Chapter 5.3 is the one that is going to introduce you exactly to the definition of an integral. The same way that a lot of your early knowledge hinged on you understanding what a limit was, from here on out in the book, a lot of what comes hinges on your understanding of an integral. So if there was one section from here on out I could get you to actually read, it would be 5.3. That is going to be crucial for you to get the rest of the material. If you can completely understand what exactly an integral is, then you'll understand it. Now, I'm not really going to follow the book. I may kind of do what we did with derivatives. You might remember way back before we even introduced the definition of a derivative, I calculated some by hand for you, trying to give you intuition for what was coming. So that is largely what I'm going to do today. I'm going to make sure we cover the book material. That stuff's pretty easy. But what I'm going to focus on is calculating some integrals by hand for you to try and establish intuition in your mind for what exactly these integrals are. So that's the big idea. So the idea of an integral is we are going to have some function, f of x. We are going to want to calculate the area of the function under the curve between 2 points A and B. That is what this notation means. Find the area under f between A and B. Okay. That's one way you can read it. It's called a definite integral. The way you literally read that is integrate f of x from A to B. Okay. But pictorially, here's what it's asking you to do. And so the idea is take that area, whatever it is, approximate it with a bunch of rectangles, and then calculate the area of the rectangles. Now I am going to, and it's completely arbitrary, for all the calculations I do today, I'm going to calculate the height of the rectangle using the right-hand point. Although this one didn't really show that. Oh, those ones I used random points. Forget about what I just said. This was a lower sum. Okay. I'm going to use right-hand points. This is using a lower sum, so it's always using the bottom rectangle. So it's always going to give you a slight underestimate. But if we keep making those rectangles smaller and smaller and smaller, we get a closer and closer approximation. And if we did infinitely many rectangles that are all arbitrarily small, then we get a perfect area. Mm-hmm. So crucial to understanding integrals is we're summing up a bunch of stuff. In fact, we're summing up infinitely many things, and so I need to give you some notation for writing big sums. So we're going to introduce sigma notation. This is notation for writing big sums so that we don't have to write big sums. So, strictly speaking, how do you read it? This says we are taking the sum from k equals 1. This tells us where we're starting our sum at. To n, this tells us where our sum ends, of some term a sub k. Whatever is here, it depends upon k there. As k changes, a sub k changes. Okay. So this is shorthand for some big sum. So what does it mean? So the sum from k equals 1 to n of a sub k is what you get when you plug in 1 for k, a sub 1, plus what you get when you plug in 2 for k, a sub 2, plus what you get when you plug in 3 for k, dot, 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 all the way until you finally plug in n for k, whatever your top number is. So this tells you where to start, this tells you where to end. Keep plugging them in and adding up the results. Okay. That's what that notation means. So let's just do some very concrete examples, try and make this very clear. So we're going to take the sum from k equals 1 to 4 of k squared. So how exactly do we do this? We plug in 1 for k.
Yeah, 1k.
What's 1 squared?
1.
1. Then you add it to what you get when you plug in 2 for k.
4.
4. Plus add it what you get when you plug in 3 for k. Plus what you get when you plug in 4 for k.
16.
16. And then you'll see that if you quickly add that up, we get 30 if I add that right.
Yeah.
So that's what this means. The sum from k equals 1 to 4 of k squared. So plug in 1, 2, 3, 4, stop when we reach that top number. And that's a shorthand way. This is a shorthand way of writing this sum.
And that's doing what that picture shows.
What this shows?
Yeah.
This is adding up areas. So right now we're just notation for adding up numbers. An area is going to be a number, which is fine. But for now, that's just notation for writing out a sum. So I don't literally need to write 1 plus 4 plus 9 plus 16. That's tedious. I could instead just write that, and it's the exact same thing.
Oh, okay.
It's just shorthand for writing sums. We're going to work up to writing out this sum, the sum of the area. And we're going to want to use this notation. So first, step away from integrals, and all we're doing is looking at this notation, trying to read this notation, trying to work with the notation.
Okay.
It's very useful notation, very commonly used in more advanced math courses. You'll see this notation everywhere. All right, let's try another one. So we're going to take the sum from k equals 3, this tells us where we start, to 6 of 2k. So what do we do first?
Plug in 3.
Plug in 3. And so what's my first number here?
6.
6. Plus, since it's sigma notation, we're summing it up.
Oh, yeah.
What do I get when I plug in 4?
8.
8. Plus,
whatever you get when you plug in
5.
5.
Which is 10. Plus
12.
12. Plus
4.
no, we're done.
Oh, my bad.
Sorry, probably blocking your view of where we're ending. So we just go from 3 to 6, and then we're done. It was just shorthand for that.
Okay. Mm-hmm.
Gotcha. Okay. Now, there's no reason that we can't have more complex expressions. It doesn't change the principle. So we're going to take the sum from k equals 0 to 5 of this thing. Now you might say, what on earth do you do with a there? It's just a constant. It's just a. Doesn't change anything. So plug in 0 for k, what do we get?
A
0.
over 1.
You get 0. You get a times 0 over 2, or over 1, which is 0. Plus, now when you plug in 1.
1/2.
Well, remember you have your a there. A times 1 is a, whatever the a is,
A halves.
all over 2, so a halves. Plus, when you plug in 3,
3.
or sorry, when you plug in 2.
2. 3.
2 times 2 is,
4.
times a is,
So 4.
4a, all over, what's our denominator?
1/2. But that's.
We're
3.
plugging in 2.
That's 3.
3. And then plus 3 squared a's, so 9a all over 4, plus 16a all over 5, plus 25a over 6 would be our last term. Make sense? And now it's also useful to be able to do the reverse. Look at some sum and try and express it with sigma notation.
Okay.
So let's go backwards now. Now this time we're trying to come up with, I guess we can erase that when we get there. This was 25a plus 6, just for completeness. Okay, so we're trying to represent this with sigma notation. So what should my k start at?
1. No,
So we'll do start k at equals 1. Now how many numbers do we have?
We have 7.
We have 7 numbers. So it's going to be k from 1 to 7. We're adding up 7 things.
Why not start at 0?
We could. We could start at 0. There's infinitely many ways we could do this and end at 6. Just make sure this number increments this, however many numbers there are here. So 0, 1, 2, 3, 4, 5, 6.
So we can do -7 to 0.
Yes, you can start -7 and go to -1, and that's perfectly fine.
Okay.
So we're going to go k equals 1 to 7 is probably the most intuitive way. Okay, now what's our first number?
1.
1, so maybe just put a k there. Let's see what that gives us. So when I plug in 1 for k, that gives me 1.
Yep.
Cool. Now when I plug in 2 for k, what do I get?
2.
But I need 3.
So add 1.
So add 1. So if I do plus 1 here, now go back to 1. When I plug in 1, I get 2 instead of 1.
Oh.
What about make k 0?
Your k 0?
Yeah.
It's not going to change the principle.
Okay, that makes sense.
So what can we do trying to represent this? This is like adding up a bunch of odd numbers. You know how to express an odd number in math?
Add up by 2.
K squared minus 1.
Now you're just throwing stuff out.
K plus 2.
But you almost said the exact thing.
No.
What about 2k minus 1?
Oh.
Notice that each of these are incrementing by 2,
Oh.
which should make us think 2k.
K squared.
And then just make your first one line up. So when I plug in 1, I get 2 minus 1 is 1. When I plug in 2, 2 times 2 is 4, minus 1 is
5 or 3.
3. And so you see now how this gives you this sum.
Yeah.
Now I'm going to write that sum. This time I'm going to start with k equals,
Alex.
nope.
Alex.
Oh yeah, sorry. Alex.
Alex.
0 to 6. The only thing that changes is put a plus 1 there.
What did you just... Oh.
So now I made it go from 0 to 6. It gives the exact same sum. Plug in 0, we get 1. Plug in 1, we get 3.
Mhm.
All the way to dot dot dot, plug in 6, we get 13.
Yeah.
Now, nothing special about that. We could have gone from -7 to -1. The only thing that would have changed is make this a plus 15. So now, plug in -7, what do we get?
1.
1. Dot dot dot, plug in -1, what do we get?
-1.
-1 times 2 is -2 plus 15 is 13. So the first one gives us that, and our last one gives us that. So there isn't the right answer to how you can express these sums. There's an infinite number of ways you can do it. In general, I'm going to stick to the practice of starting at 1 and counting up to wherever we're counting up to.
7.
So that will be my own personal way of writing it. But there's nothing correct about that way.
Wouldn't that change it back to +1?
Oh yes, which would make this back to plus 1. So it just changes your constant there. What that constant is that you add up, depending on where you're starting. Okay, so now, some useful formulas. Here's the problem I'm going to give you. I want you to add up all the numbers from 1 to 1,000. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, all the way up to 1,000. What does it equal? And we're going to come up with a quick formula for doing that. First, to just grapple with this thing, let's write that out. So we're talking about the sum from k equals 1 to 1,000 of just k. There we go. We wrote out the sum, rather than tediously writing this all out by hand, which would have been really annoying.
Yeah.
And what does this equal? This equals 1 plus 2 plus 3 plus dot 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 plus 999 plus 1,000.
Doesn't it add 1 every time?
Yeah, that dot 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 means follow the pattern all the way.
Oh, okay.
Good so far? So there's writing out our sum. Imagine I wanted to figure, let's start out by looking at what double this sum equals. You with me?
Okay.
So if we have 2 of those sums, then it's the exact same thing. Let me write this a little bit different. We're going to start at k equals 0. That doesn't matter,
Okay.
because then I just added 0. So this is going to be, k is going to be equal to 0 plus 1 plus dot dot dot, right? Didn't change anything. Now calculating 2 of those, I'm going to rewrite out the sum, but I'm going to rewrite it out in backwards order. Let me get more space here. 0 plus 1 plus 2 plus dot dot dot. Maybe we can do 3 plus dot 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 plus. Okay. So now, since we have 2 of them, I have this sum again. So I'm going to write it out again, just in reverse order. I'm going to write my 1,000 right here, plus my 999 right here, plus my 998 right here, plus my 997 right here, plus dot 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 plus 1 plus 0. You see it?
You can write it in whatever order you want, doesn't matter.
Yeah, it doesn't matter what order you add in. Addition is commutative. You with me? What's 0 plus 1,000?
1,000.
1,000. What's 1 plus 999?
1,000.
1,000. Plus, what's 2 plus 998?
1,000.
1,000. And we see that it's 1,000 plus 1,000 plus 1,000 how many times?
1,000 times.
Is it 1,000 times?
Yeah.
Yeah.
It's 1,001 times. Because you have 0, 1, 2, 3, 4, 5, 6, all the way up to 1,000. So there's 1,001 terms written out here. If we start at 1, there's only be 1,000 terms written out there.
Would it be 1,002 then? Because you have to do that twice.
No. There's 1,001 terms here. There's 1,001 terms here. Add them together, and I've got 1,001 terms. You with me? So this total sum comes out to 1,001 times 1,000. We have 1,001 times. You with me? That's what 2 of those sums equal. So what does a sum equal? Just divide both sides by 2. It equals that over 2. Or in other words, it equals 500,500, adding up all the numbers from 1 to 1,000.
5,500.
500,500. 500,500. All I'm doing is I'm taking 500 times 1,001. Gives me 500,500.
Yeah.
Okay, there we go. Adding up all the numbers from 1 to 1,000. Now, there was nothing special about adding up from 1 to 1,000. What if I would have added up from k equals 0 all the way to n? Well, then that would just 1 plus 2 plus 3 plus dot 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 n minus 1, whatever that is, plus n would have been our last number, right?
Yeah.
And if we would have done 2 of them, then this would have been an n, this would have been an n minus 1, this would have been an n minus 2, this would have been an n minus 3, plus dot 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 1, 0. And when we added them all up, what did we get in this row? What's 0 plus n? N. What's 1 plus n minus 1? N plus n plus n plus dot 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 plus n plus n. How many n's do we get?
N plus 1.
N plus 1 n's. So 2 of them gives me n plus 1 n's. So one of them would have just given me n times n plus 1 over 2. So the sum of all the numbers from k equals 1 to n of any number n you choose is just n times n plus 1 all over 2. So if I would have instead asked you to calculate the sum of all the numbers from 1 to 100, how would you do that? It's just 100 times 101 over 2. Or in other words, it's 5,050. Just plugging into that formula.
Yeah.
So that's how you can quickly do sums. Now, what if I would have had you do k squared? Unfortunately, we don't get to prove these. We need proof by induction. They're not hard proofs. If we were doing proof by induction, these would be standard proofs that we start with. But I don't have time to teach you guys proof by induction. So the result is n times n plus 1 times 2n plus 1 over 6. So if I wanted to add up 1 plus 4 plus 9 plus 16 plus 25 dot dot dot, adding up all the squares from the first square maybe to the 100th square, just plug in 100 to this and that tells you what the sum of the first 100 square numbers is. You with me? And then for cubes, we also have a formula. It's just n times n plus 1 over 2, all squared. Funnily enough, this is just a square of this.
Yeah.
You with me? Okay, so there's adding up some perfect sums. Remember, we're going to be doing big sums where we need to add up n things. And so we're going to be using these three formulas to help us quickly add things up. When you calculate integrals by hand, you need to use these types of formulas.
Okay.
Now these are the only three formulas that we're going to introduce. We won't be doing integrals of anything bigger than a cubic by hand. So these will be the only three formulas that you use. But with those formulas, you can start solving most of the interesting things we care about. Okay, so some properties that this sigma notation has. So first off, looking at this, the sum from k equals 1 to n of a sub k plus b sub k is equal to the sum of all these terms plus the sum of all these terms.
Yeah.
So the sigma of a sum is just a sum of the two sigmas. Let me write this out.
Isn't that just distributive property?
Oh, well, do this to help you see it. So really quick, I'm going to write this one out. So this is like that. Here's my a sub k term, here's my b sub k term. With me? Now it's not the distributive property, it's just a commutative and associative property. So let's really quick run this out. When I plug in 1, what do I get?
1, 2.
We're going to keep it separated to help us see it. So it's 1 plus 1 squared. You see that? I'm not going to simplify anything. Plus 2 plus 2 squared plus 3 squared. They're just blindly writing it out, right? Now, this is the same thing as, I can do the 1 plus 2 plus 3 first, group those together, and then I can do the 1 squared plus 2 squared plus 3 squared second. You see that? That's all this is saying. So summing up the first term here and the first term here together, pairing them together like this. This way is pairing them like this. This way is splitting it into two sums. Doing all your a sub k's first, and then doing all your b sub k second, doesn't matter. So a way that we can split up the sums. That would make sense?
Yeah.
Okay, what if we had a minus here? How does that change it?
Same thing, just with the subtraction.
Very similar idea. So this is going to be minus, this is going to be minus, this is going to be minus, right? And now, we can write that as positive 1, positive 2, positive 3, subtract 1 squared, subtract 2 squared, subtract 3 squared. And so the sum of all your a sub k's minus your b sub k's is just the sum of all your a sub k's minus the sum of all your b sub k's. And you can split up differences just like that as well.
Cool.
Let's try another one. Let's see. What's the best way to see this? Let's say that we were looking at the sum from k equals 1 to 4 of just k squared, you know what that would equal. That would just be 1 squared plus 2 squared plus 3 squared plus 4 squared, right? Now imagine, rather than k squared here, I instead had some constant a times k squared.
Okay.
Then what happens? We would have an a multiplied to each of these terms. It would have been a times 1 squared, a times 2 squared, a times 3 squared, a times 4 squared. You see that?
Yep.
Now I can rewrite this as just factor all my a's out, and that would have been 1 squared plus 2 squared plus 3 squared plus 4 squared. And now let's write this sum using sigma notation. So this is equal to a times the sum from k equals 1 to n of k squared. That's just, or not n, sorry, 4. Just rewriting this like that.
So those two mean the same.
So the whole point here is you can factor your a out of your sum. So if I have the sum of some constant times my a sub k terms, I can pull that c out, and that's just factoring a constant out of the sum. Since that constant applies to every term in the sum, you can factor it out of every term and factor it out of the sum altogether. That one make sense?
Yeah.
Okay, let's try one more. Calculate this one. Now, let's calculate this one. You tell me what the sum is. Let's do the sum from k equals 1 to 4 of some constant a. What is that going to be?
A every time.
So what is it?
0.
What? Plug in 1 for k, and what is this?
It's
It's a. Okay, now plug in 2 for k, what do we get?
A.
A. Now plug in 3 for k, what do we get?
A.
A. And plug in 4 for k, what do we get?
So we get
A. So we get 4a.
Oh, I see.
You see that? Now imagine that we had an n right here.
You get NA.
Then you just get n times a. So the sum of some constant n times is just n times that constant.
Okay.
So the sum of some constant n times is just n times that constant. Now here's a mistake that you are going to be tempted to make when you do these, which is forgetting to treat n like a constant. So let me write one more out. This will be kind of a gotcha. What's the sum from k equals 1 to n of n?
N squared.
It's just n squared. It's just n plus n plus n plus n plus n times. Or it's n n's. Or it's n times n or n squared. Because it's not dependent upon the k. Remember that the n up there is just a constant. Good? So as some exercises, let's quickly write these ones out. Oh, I guess we already did one of them. We just barely figured out this. The sum from k equals 1 to n of n, we already figured out that's n squared. Okay, let's look at this one and figure out this one's sum. We're looking at k equals 1 to 3 of this thing.
Okay, 1, 2, 1 sec. 3, that's 1.5.
So first off, let's just factor out the 1/6. So this is the same thing as 1/6 times the sum. How do I know I can factor out the 1/6?
What's your pull your constant out?
That's using this rule. If you have c times a constant in the sum, you can factor out.
Why do you need to? Why can't you just plug in?
You could, but I don't want to deal with 1/6 every time we plug in. I mean, I know we're only adding up 3 terms here, but imagine we were adding up 30 terms. I don't want to deal with 1/6 on every term I deal with. Let's deal with 1/6 when it's all said and done. So I'll pull the 1/6 out, and then what do we got? We've got 2k plus k squared. And then just to completely drive the point home, this is the exact same thing as 1/6 times the sum, maybe put parentheses here, times the sum of 2k, k equals 1 to 3, of 2k plus the sum from k equals 1 to 3 of k squared. Right? Just split the sum up. Now you might wonder, why are we doing that when we only have 3 terms here? Imagine I instead have like an n here and ask you to figure this out. Now this would be an n,
Yeah.
and this would be an n. And how on earth would we figure this out? Let's keep going in the n scenario. So now finally, I can write my 1/6 here. Pull the 2 out of this one.
Yeah.
So what's 2 over 6?
3.
1/3. So I have 1/3 times the sum from k equals 1 to n of k, plus 1/6 times that, 1/6 times the sum, k equals 1 to n of k squared. You with me?
Yeah.
And now what is this sum? It's right here. And what is this sum? It's right here. And so you can solve this in this completely general case. You with me?
Yeah.
Yeah.
So what is this sum? That's n times n plus 1 over 2. So I'm going to take that sum and multiply it by 1/3 in the bottom. That would be equal to n times n plus 1 all over 6 divided by 2, but times 1/3 gives us that.
Yeah.
Plus this sum is n times n plus 1 times 2n plus 1 all over 6, but times 6 is 36.
Oh, okay.
And now you can work out the algebra from there if you wanted to. I'm not going to keep messing with it. You see that?
Yeah.
Okay, so there's using our rules, and you can now do this sum for any n number of terms. You can come up with the formula.
4n.
For any n you put here. We started out in a special case of 3 just to help you think. But we could do that for any n that you put up here. So if I want to add up terms like this all the way up to 1,297, you just plug in 1,297 for n there, and there's a sum. You don't need to sit on your calculator manually plugging in 1,297 numbers. That would be a very stupid thing to do.
Yeah.
So now you know how to add in much more intelligent ways. Not only simple sums, but even something more complex where the pattern's hard to just say, here, add up these numbers.
Okay.
You see it? So, last one. Let's calculate what this one is. The sum from k equals 1 to n of k squared plus 2k over 7. Now I'm going to do the algebra in one go. This k squared is being multiplied by 1/7. So that's 1/7 times the sum from k equals 1 to n of k squared, plus this one's coefficient is 2/7 times the sum from k equals 1 to n of k. You see how I went from there to there? 1/7 k squared is this term. 2/7 k is this term. And now you can replace the k squared with this, and you can replace the k with that. And I give you your formula.
Yeah.
So then it's equal to, let's see, k squared is the one over there, so that's n times n plus 1 times, is it 2n plus 1? Okay, I've been doing it right.
Oh.
2n plus 1, all over 6, but then times 1/7. What's 6 times 7?
35. Or
42. Made me hesitate, wonder if I was crazy. Plus, over here, we have n times n plus 1 over 2. We'll include the 2 there really quick. 2 times n times, well, we don't need that parenthesis, times n plus 1. The 2 here was over 7. The n times n plus 1 was over 2. So those 2's cross cancel, leaving it just over 7. You see that? And then you can keep doing the algebra if you wanted, but that shows you the idea.
Okay.
So we can solve these sums for any arbitrary n. And that would be like the hardest problem you were asked to do. Something like this. It won't get harder than that. Most of them will be more like this, where you spit out an actual number. Some of them will have you spit out a formula in terms of n.
Alright.
Good? Okay. So now moving on to integrals and calculating some integrals by hand and using sums to do it.
Just the next section.
No. This is not any of the sections. This is me doing what I said I was going to do, which is jump ahead to calculate some integrals by hand to give you intuition. We've already covered everything that you need for your sections.
Okay.
We have one more example that I want to do from your sections. The homework is going to be much easier than the stuff you see me doing.
Okay.
I want you to see where it's going and why the author is making you calculate all these areas. So now, let's look at this function, x plus 1.
Okay.
Here's the function, the blue line graphed out. And what we are going to do is we are going to calculate the area of this function between 0 and 3, the area under that curve.
Okay.
Now I'm intentionally picking one that we already know how to calculate. Let's quickly calculate this the way that we know how. First off, notice that this area right here, we can split this up into a triangle on top and a rectangle on bottom.
Yeah.
What's the area of this rectangle with a height of 1 and a base of 3?
Area.
Yeah, what's the area of this piece?
Base times
I don't know
height.
base.
So,
Base times height. The height is 1.
so 3.
Yeah, it's just 3. Plus, now we need the area, maybe put that there to help you see. Now we need the area of this triangle. That triangle has a base of 3 and a height of 3. What's the area of a triangle? 1/2 base times height, or 1/2 3 times 3, or 9/2.
Oh, so you already know them.
Yeah, I'm intentionally picking one that we already know the area of to help us keep track of the process.
Alright.
You with me?
Yes.
So 6/2 plus 9/2 is 15/2. So we already know that the area of this is 15/2. Let's scribble that up in a corner somewhere.
Okay.
That's what we already know. Now first off, I'm going to do the approximation way that we won't bother calculating, and then I'm going to calculate the actual integral by hand, and we're going to get exactly 15/2. Okay, so first thing I'm doing is I am going to divide this up into 8 even pieces. My picture's lying a little bit. You with me? And we're going to calculate the area of each of those rectangles. You with me? So first off, what is the base of this rectangle, our first rectangle? What's its base? I took this and I divided it up into 8 even pieces.
3 over 8. Or
1.
3 over
3/8. I took this distance of 3 and I divided it up into 8 even pieces. So the base of this rectangle is 3/8, 3/8, 3/8, 3/8. If I have 3/8 8 times, then my total base is going to be, what's 3/8 times 8?
8. 3.
Yeah, 3/8 times 8 is going to be 3,
3.
which gives me my total distance there. Is it obvious to your intuition that we're doing 3/8?
Yeah.
We good? All right. So 3/8 is that little width. I'm going to add up the base times the height. So 3/8. So this point right here, its coordinate is 3/8.
Yeah.
That thing's coordinate is exactly 3/8. That's the coordinate of this thing. And that's also the width of this rectangle. So our sum here is, we are going to do the base of the rectangle, the base, 3/8, times, now the question is, what's the height?
Varies.
Well, what's the height of this rectangle?
1.
It's the height of, no. It's the height of our function. Notice that I chose the right-hand point. It's the height of our function at 3/8.
Oh.
What is the height of our function at 3/8?
It's 1/8.
How is he getting that? He's doing 3/8 plus 1. That's what f, maybe write this explicitly. What is our function? Our function f of x is equal to x plus 1. That's this blue line.
Oh.
What does this give you? This gives you the height at any point x. If you plug 1 into the function, it spits out 2, because the height at 1 is 2. If you plug 3/8 into the function, it spits out
11.
3/8 plus 1, or 11/8.
Yeah.
You with me? So this would be just, I'm going to write it this way, 3/8 plus 1, just to help be super explicit. You with me?
Why? Oh.
It's f, oh, sorry.
Why is the F there?
I'm just going to leave it as f of 3/8. Where this is f. Just plug in 3/8 and it spits out 11/8.
Okay.
You with me? Okay. Now, let's look at our next rectangle. So that's our first rectangle. Let's make sure that this works up for our next rectangle. So now I'm looking at my second rectangle here. What's the base of my second rectangle?
3/8.
It's still 3/8, so it's still a base of 3/8. But now what is the height right there?
F of.
Or what is this x coordinate? Maybe let's say, what's that x coordinate?
It's gonna be.
This x coordinate was 3/8, so that one is
6/8.
6/8, or 2 times 3/8. just to keep it clear what your thinking was, right? And then what is this coordinate? 3 times 3/8. And this is 4 times 3/8. 5 times 3/8, 6 times 3/8, 7 times 3/8, 8 times 3/8. Or in other words, 3. 8 times 3/8 would be 3. So in general, for our cake rectangle, let's say this is our cake rectangle, its base is 3/8, and what is its height? For our cake one. Not our first one, not our second one, but for our cake one.
It's f of your base.
It's just going to be k times 3/8.
Oh.
Oh,
If k means our third rectangle, then it's 3 times 3/8. If k meant our 8th rectangle, then it would be 8 times 3/8. If k meant our first rectangle, and so our formula here is this. Those areas are the base times the height for all 8 rectangles that we're summing up over. You with me? Okay, now we're going to redo this process, but rather than using some fixed number 8, we're going to use n of them, rather than some hard-coded number 8. So now let's look at the sum, and just to be super explicit in case you weren't seeing it, this is going to be equal to 3/8 times f at 3/8 plus 3/8 times f at 2 times 3/8 plus dot 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 plus 3/8 times f at 8 times 3/8. Right? That's what that was. And that's the type of thing that your first section is going to have you do, is just approximate areas with rectangles. But now we want to get the perfect area,
Oh, you have to
because
write,
this is going to be an overestimate.
don't you have to write that all out then?
Yeah, we could plug that all into our calculator, and it would spit out some big number, and it would give us our approximation. I'm not going to plug all that into the calculator and spit out our
But that's
approximation.
what they're asking.
But that's what a bunch of the first problems are going to ask you to do, is just approximate area using 8 rectangles or something like that.
Okay.
You don't have to overthink it this much, but this is definitely much harder than what you'd be asked to do. Okay, so now let's do it for n rectangles. You with me?
Yep.
So we're looking at the sum from k equals 1 now to n. We're going to add up n of these rectangles.
I was going to say, why don't you just put infinity up there? And
Well, one step at a time. But you see where we're going.
Yeah.
Okay, so now, if I have n rectangles, what is the base of my rectangle? 3 over n.
3 over n.
This total distance is 3. If I'm dividing it up into n even pieces, each of those rectangles is going to have a base of 3 over n. You with me?
Yes.
So our base is 3 over n times, now we need our height.
Is just.
What is our first coordinate point right there? How far over is that point?
It's 3 over n.
It's 3 over n.
Right.
How high is our second point? Or how far over is our second point?
2. 3 over n.
2 times 3 over n. And for our cake rectangle, how far over is its right-hand point?
It's just k 3 over n.
It's just k times 3 over n. For our cake rectangle. You with me?
Yes.
So this is times f times k times 3 over n. Good so far? Now we're actually going to do what Jeremy was hinting at. If we're going to get a perfect area, how many rectangles do we need? Infinitely many. So we are going to take the limit as n approaches infinity of this thing. And that will give us the area perfectly. That's a big idea. That's the whole idea of an integral. You're basically looking at the definition of this integral right now. That's all it is.
Using that exact.
This exact limit, and we're just going to calculate it. So we're actually going to calculate this whole thing, and it's going to come out 15 halves.
So how would you do that?
Right, so this time I'm going to show you all of the nitty-gritty algebra. No skipping steps. We're going to see the whole thing. Okay? So, let's keep going. First off, n is a constant. And 3 is a constant. So I'm going to pull the 3 n's out of the sum.
Okay.
So, and we're going to take our limit when it's all said and done. So, the limit as n approaches infinity, put our bracket here. I'm going to save it this equals and then finally calculate our limit. You with me? So just looking at what this piece right here equals, we're going to pull the 3 over n out. And this is going to be times the sum
of n.
from k equals 1 to n of, now let's plug this into our function.
Oh, for that, but that's only that example specifically.
Yeah, our function, we have, if we're going to get an exact area, we need an actual function that we're talking about.
Okay.
So our function is x plus 1. So plug that in for x, and we get
K times 3 over n plus 1. That's it.
well, so far, we got to keep messing with this.
Yeah.
Okay, so now this is equal to, I'm going to pull my 3 nths, and I'm going to split this into 2 sums. I'm going to sum up all these terms and sum up all those terms using this rule. The sum of 2 terms, the sigma of a sum is the sum of the sigmas. That's the idea. So this is going to be equal to, for this first sum, I can pull another 3 nths out. So put a square bracket right there. For this sum, I can pull out another 3 nths. And that is times the sum from k equals 1 to n of k, plus this sum was just, maybe put parentheses here so you don't think that it's inside the sum still, plus the sum from k equals 1 to n of just 1. You see how we split that up? You see the algebra there? We have 3 nths times the whole thing, whatever that is.
Yeah.
This piece is just pull the 3 nths out of its sum, adding up all the k's, and then this piece is just adding up the 1s n times. Good?
Yeah.
Okay, so let's calculate this. This is equal to 3 nths times 3 nths is going to be
3n squared.
9 over n squared times, what is the sum from k equals 1 to n of k? N times n plus 1 all over 2.
Where do you get to? Oh, plugging in there.
Just using those formulas. You have to, when you calculate these integrals by hand, you are going to have to be using one of these formulas. No way around it.
Okay.
Unless it's like a constant function. Okay. So that was this sum. What is 1 plus 1 plus 1 plus 1 n times? Just n.
Yeah, just n.
N, but we have times this 3 nths. So plus
N times
3 over
3
n,
over
n.
And then you can't take that out.
Yeah, those are going to cancel out to just 3. It turns out that that 3 is the same 3 for this area right here.
Oh.
That came from this plus 1, which was the 1 up shift. So that's what that 3 corresponds to. So this is going to be equal to, over here, I'm going to cancel out an n top and bottom.
Okay.
So we're going to be left with 9n plus 9, distributing the 9 across both those. All over, in the denominator, we have 2n, because we cancel out one of the n's top and bottom. Following the algebra there? And then this is just plus 3. Now, I'm going to split this up into 2 fractions. So 9n over 2n is the same thing as
9n over 2n.
9 halves.
9 halves. Plus, this is still 9 over 2n,
Yeah.
plus 3. You with me?
Mm-hmm.
Now, we're taking the limit as n approaches infinity, so let's take our limit now. What's 9 halves as n approaches infinity?
9 halves.
And 3 is?
3.
And 9 over 2n as n approaches infinity?
No.
Basically
Oh,
nothing.
no, wait.
0. It goes to 0.
Not bad.
Oh, I remember.
So what's 9 halves plus 3? Or what's 9 halves plus 6 halves?
15 over 2.
15 halves. Shocker, shocker. This piece corresponded to that triangle. This piece corresponded to that rectangle.
So what if that added up to infinity instead?
It couldn't have.
What if the n?
Because we added up the area under this curve, which is a number. So if we got infinity coming out of this, we know we messed up.
Yeah.
Well, I'm saying, what if your n is on top?
Then you messed up.
Then you can't take it the limit.
You can always calculate the area of that thing. If you're getting infinities, you messed up your algebra. It's not that math is wrong, it's that you messed up. The area is a fixed area.
Yeah.
Now, if I try to take the area of this function from 0 to infinity, well then yeah, the area is infinity.
That's really right.
No.
Oh.
We'll eventually talk about Gabriel's horn. Gabriel's horn is infinitely long. It's a horn, like a trumpet that you blow. That's the shape of it. It's infinitely long. It has infinite surface area, but a finite volume. So in other words, if you want to paint the horn, you need an infinite number of paint. On the other hand, you could fill up the horn with just a gallon of paint. Just intuition.
Oh, that's so weird.
So we'll get to that. I think that might be a Calc 2 concept. I think we get to it, but I'm honestly not sure. Okay, so we calculated that integral by hand. That was fun.
Yeah.
We're gonna repeat now with just a different one that's a little bit more complex. Same exact process, gonna walk you through it all over again.
Okay.
Good? So now here's our new function. Our function is 4 minus x squared. It's a parabola pointing down like this. You with me?
Mm-hmm.
Okay, and we're going to do the exact same thing. We need to sum up the areas of rectangles. So I'm going to divide this thing up into n rectangles.
Infinite times.
Well, first we'll just divide it up into n, and then we'll take the limit. Right?
Mm-hmm.
So it's easier to start by thinking about, let's divide this up into n pieces. Say n's 10 or 5 or 7, doesn't matter. So we're looking at the sum from k equals 1. Again, starting from 1 only corresponds to the fact that I'm picking this right-hand point. If I were picking the left-hand point, everything's the same. The only difference is I would have done k equals 0 to n minus 1. And all the math comes out the same. And that would have been using the left-hand point.
Okay.
Because what's the left-hand point right here?
0.
0. Plug in 0 for k, we got 0. What's the left-hand point of this rectangle? It was the right-hand point of the previous rectangle.
Mm-hmm.
So that's what you get when you plug in 1, etc.
Oh.
And if you have calculated all the limits, they all come out the exact same. Doesn't change anything.
Mm-hmm.
I just think it's easier to work with an n than an n minus 1. So that's why I personally go from 1 to n, which is using the right-hand points. So I'm going to keep to that convention. There's nothing special about the right-hand points. We could have gone through all the algebra of using the middle points. We could have gone through all the algebra of using the point that's 1/3 over in each rectangle. It doesn't matter which point in the rectangle we use to get the heights. Because as our rectangles get arbitrarily small, all that matters is you pick some point that actually gives you a height.
Yeah.
Yeah.
Okay, anyways, so doing this one. So what is the base? If we evenly divide this thing up, what's the base of each of those rectangles? What's this total distance right here?
We don't know.
2. So we're going from 0 to 2 is how we're calculating our area.
Yeah.
So what's this total distance?
N halves.
2. So what is the distance of one of those?
N halves.
N halves? What if n's 1,000? You're saying that that distance is 500?
No, it's
Sanity check.
2 over.
2.
2 over n. We're taking 2 and we're dividing it up into n pieces. That's the base of each triangle,
Yeah.
or rectangle. With me?
Yeah.
Now, what is the height? The height is f at, let's see, what's the height of this first one?
It's
2n squared. 4 minus 2n squared.
Well, sorry. What is the point that we use to calculate the height?
Oh, it's 2n.
What is that point right there?
2 over n, sorry. Isn't it?
2 over. Yeah.
Yeah, for our first point, it is 2 over n. What about for our second point?
That's k 2 over.
For our second point, it's 2 times it. And so if we go to our kth rectangle, which is this one right here, whichever one, doesn't matter, then the point right here that we would use is k times 2 over n. So we're taking the height at k times 2 over n. You broke me. All right. So it's just a base times a height, and we're adding it all up. That's it.
Mm-hmm.
With me? Now let's calculate that sum. What is that sum? Well, this is, let's pull the 2 over n out since that's a constant.
2 over n.
2 over n is just constant, pulling it out.
Yeah. And then
And then, oh, you were just saying it.
sigma n.
The sum from
K
k
equals
equals 1 to n of, plug that into our function. So it's going to be 4 minus,
4 minus.
hopefully you're okay with me just writing this. Tell me if I'm scaring you. Just plugging that in for x squared. The 2 gives us a 4, k times k gives us k squared, n times n gives us the n squared, and we're subtracting it.
Yeah, that's good.
Good? Okay, let's split this up into sums. So I'm going to do the sum of this thing minus the sum of this thing. So the sum of this thing,
Is
we can actually calculate that. What's 4 plus 4 plus 4 plus 4 plus 4 n times?
And 4. Add 4.
4n.
1.
Now times it by 2 over n.
Um,
Is that too much in one go?
You get 8 over n, don't you?
No, so the sum of this is 4n. So that's 2n times the sum of this first thing, minus 2n times the sum of the second thing.
yeah.
Okay, the sum of the second thing, let's pull out its constant. Its constant is 4 over n squared. So let's pull that out. And the sum we're left with is a sum from k equals 1 to n of k squared. You always and forever, when you're doing these, you're pulling everything out except your k's.
K squared.
Because once we just have the k's in it, you're either going to have that, that, or that. And you know how to calculate those sums.
Isn't k over n?
Did I mess something up?
Wouldn't it k squared be over n squared too?
No, I pulled the n squared out. It's right there. The 4n squared is right here, and I left the
Can
k
you do
squared.
that? Okay.
Yes, this is just a constant. Look, 4 over n squared times k squared, that is the exact same thing as 4 over n squared times k squared, right?
No.
Oh yeah.
And then that's just a constant pulling it out, so it's
Yeah.
just this exact rule. If you have a constant times each term, that's the same thing as a constant times the sum of the terms. Okay, are we good with the algebra? Okay, so let's keep evaluating it. Now you'll notice that n's go out top and bottom.
Yep.
And so we're left with
8.
8, thank you. Minus over here, 2 times 4 is
8.
8 over n cubed times this sum. Now, just notice what the math is doing here. The math is ultimately, it's kind of like it's taking the area of this rectangle and then we're going to subtract away something to be left with this area. That's what it looks like it's doing to me. Strange.
Okay.
Anyways, what is this sum? Tell it to me.
Just
N
add
times n plus 1 times 2n plus 1 over 6.
Good? And now this is equal to 8 is still just 8.
minus
Pull the 8 and the 6 together. 8 over 6 is the same thing as
4 over 3.
4 over 3. Times, now I'm going to put the n cubed down here.
Okay.
So times n plus 1 times 2n plus 1 all over n cubed.
Can you just cut them out, or do you have to distribute?
I don't know if you could just see it. Because now, ultimately, what are we going to do? We're going to calculate the limit as n approaches infinity. Right? So for our area now, our area is going to be, I better multiply this all out. I'm afraid I'll lose you. So our area is going to be the limit as n approaches infinity of this whole thing. I'm going to do some simplifying as I write it.
Okay.
So we have 8 minus 4/3 times, in the top, what do we get? So let's count all our n cubed terms. I get n times 2n gives me 2n cubed. Okay, so I distributed, basically I'm going to distribute each of these into each of those and multiply by n as we go. So I did this one. You with me? So now let's do this one. 1 times 2n is 2n. Now multiply that, n gives me plus 2n squared. See it? Now I need to multiply my n to my 1.
Which is
n times this n gives me
n squared.
n squared. And then finally the 1 to the 1 gives me
2.
1. 1 times 1 is 1. And then multiplied by the n gives me plus n over n cubed. You see it?
Mm-hmm.
Okay. So that now is equal to 8 minus 4/3 times, let's see, I'm going to write each one of these over n cubed and split this up into 3 sums. So 2n cubed over n cubed is
10 cubed.
2.
Oh, yeah, 2.
Now, 2n squared plus n squared is 3n squared, so let's combine those. 3n squared divided by n cubed.
Just 3 n squared divided by.
3n squared over n cubed. Over n cubed. But you see how the n's go out top and bottom, leaving you just 3 over n. You follow all that?
Couldn't you have factored out way before you wrote out the limit and all that? So the line right above where you're writing.
Up here,
Factored out n,
factored out the n.
She
Yes.
said factor out n cubed.
just to make, would that make it simpler or?
Yes. I wish I would have looked at that. We should have, right at the beginning, crossed out that n with that, leaving an n squared. That would have been smarter. Okay. Yeah. Would have been much better, but we didn't do that. So, messy algebra. We accounted for those two terms. Now we got n over n cubed, which is the same thing as 1 over n squared. You see it? Okay, now let's calculate our limit of this whole thing as we go. So the area is equal to, the limit as n approaches infinity of 8 is 8. And we're going to do minus 4/3 times the limit of the inside. What's the limit of 2 as n approaches infinity? 2.
0.
0.
0.
0. So it's just going to be minus 4/3 times 2. Or in other words, it's going to be 8 minus 8/3, which is the same thing as 24/3 minus 8/3 leaves us
16/3.
16/3, which is the correct answer. There we go. We perfectly calculated that area.
16/3 what? Just a number.
Right now it's just 16/3 because there's no units on there. So yes, area is just a number until you add units.
Gotcha.
Good?
Yeah.
Okay. So now in general, so that you can see the general formula for how you would do this for anything. Again, you will not have to calculate these by hand yet, but here's the formula to calculate these by hand in general. We're going to write it out.
Okay.
That's kind of taking up our space. So this was equal to 16/3. Okay. So now we're going to do this in a very general way. This integral is going to equal the limit as n approaches infinity of the sum from k equals 1 to n of, and let's figure it out in a generic picture now. So we're splitting up this area into n rectangles, right?
Mm-hmm.
And then we're going to come over here and look at the kth one and see what we can say about the kth one. So here's our kth one. Okay, so first off, if I divide this up into n pieces, what's the base of this rectangle? What's this total distance?
We don't know. 8.
It's b divided by n.
Almost. Those ones all happen to start at 0. I shouldn't have done that. What is this total distance?
8 plus
minus
b.
A.
Or
B minus A. What is the distance between 8 and 3?
Oh, yeah.
5. How did you do that? 8 minus 3. What's the distance between B and A? It's just B minus A. So my total distance here is B minus A, and I'm dividing that up into
And parts.
n pieces. So what is the base of just this triangle right there?
The rectangle?
Or rectangle. I keep saying triangle for some reason.
b minus a over n.
Just B minus A over N.
Makes sense.
The total distance divided by how many pieces we're breaking it up into. So our sum here, we're going to take the base, which is B minus A over N, and we're going to multiply the height, which is going to be f of, f depends upon our function here. So now we're writing it in a very general way. So, I don't know why I'm writing so massive. So that is b minus a over n times f of. Now, what is, so we know the length of each one of these is b minus a over n. What is this right-hand point right here? What is the coordinates of that point?
B minus
A plus 1.
plus
Not a plus 1.
A plus b minus a over n.
Perfect. It's just a plus b minus a over n. A gets us from 0 to here. B minus a over n gets us from here to here. What is the coordinate of this next point?
It would be a plus
A
k.
plus 2
A plus-
times b minus
A plus 2 of those distances.
Yeah.
And now for our caked one,
A plus K times B minus
a plus k times whatever our base is, b minus a over n.
Gotcha.
And so that's exactly what it is right here. And so this limit is exactly how you can calculate now the integral by hand of whatever I gave you. As long as I give you the function, and I tell you what the b are and the a are, where to start and where to end, that formula is exactly what you use to calculate the area.
So we don't need to go through all of that work.
Well, yes, this is exactly what we have written here for this special case.
Right.
This is a formula for setting it up. Here we plugged in this. What was b minus a? 2. What was n? N. What was a? 0. What was k? K.
Yeah.
Similarly for what we plugged in right here. It's just plugging into that formula. So there it is in general for anything I give you. So you don't have to keep rethinking through it from scratch every single time.
So that's the definition of it.
Almost. This will always give you the area. This is not the definition. If this limit exists, it does give you the area. But this is being kind of restrictive. Why is this being kind of restrictive? First off, do I have to perfectly divide this up into even pieces every time for this to work?
No.
Yes.
No. I don't know.
Does it matter that all my rectangles have the exact same width?
No.
Yeah.
Wow.
For the k part.
Well, imagine I just did infinitely many rectangles, but some of my rectangles were bigger, some were smaller.
Yeah, it does matter.
No,
because
it
of
wouldn't
k.
matter because they're all adding it.
They're all
As long as all my rectangles are getting arbitrarily small, does it really matter that each of my rectangles are the same size as the other one?
No.
Yeah, because of your k.
Forget our formula here. We're just talking about the approach. So imagine now, here's how I decide I'm going to approximate the area. Rather than evenly dividing it up, I am instead going to start by splitting it like this. So that's going to be the first way I make my rectangles, something like this. There's my first approximation. And then my approach from here on out is to split this in half, split this in half, and split this in half. And then use those rectangles. And then split all of them in half again.
Oh, there's different.
Notice that these rectangles are always twice as long as those ones.
Okay. Yeah.
But all the rectangles in the limit are going to get arbitrarily small.
Well, we don't even have to use rectangles, do we?
We don't even have to use rectangles. We could make the tops slanted if we want.
Like trapezoids?
And use like trapezoids. And that would also work. So why do we use rectangles? Because it works and the math is easy. Writing out the math for this would be a nightmare. You could do it this way. There's nothing wrong with that. It's just really ugly. It's like you would first need to calculate those ones separately and then calculate those ones. And that would be the way you'd have to do it mathematically, which is hairy. So this isn't quite the definition of an integral, because with an integral, it doesn't matter how we take these rectangles as long as their bases are going to 0.
Right.
Mm-hmm.
And so what we are doing here is we're partitioning up this interval. I'm partitioning up the base every time I add an interval. You with me?
Yeah.
So introduce you to exactly what a partition is. So what we are doing is we're picking these points at the base to construct our rectangles from. That is creating a partition. So a partition is the set of points where our first point is A and our second point is B. And then the next point always comes after the previous point. So my first point, second, third, fourth, fifth. I can't do fifth, sixth, seventh, eighth. You can't alternate back and forth like that. So a partition is just a sequence of points you use. a partition on AB is just a sequence of points where the first point is A, the last point is B, and the kth point comes after the k minus 1 point.
Okay.
It's always a big number, so it increments as you go. No going back and forth. So that's what we mean by a partition. So, writing it out explicitly, here we have some partition on this. Here's x sub 0, here's x sub 1, here's x sub 2, here's x sub 3, dot dot dot, here's x sub k, dot dot dot, here's x sub n. There's a partition on that interval.
Mm-hmm.
Notation, what now is the length of each of these little inner rectangles? If they're all sorts of different, if I'm not guaranteed that I'm evenly spacing every time, then what is the base of this rectangle right here?
Previous subtract.
It's just x sub 1 minus x naught, right?
Yeah.
So the base of our first rectangle, which is what we mean by delta x1, is just the end point minus the start point.
Mm-hmm.
Delta x2 is just the end point minus the start point. Delta xk is just the end point minus the start point. You with me? And now, dividing it up however I want, as long as in the limit it's still going to 0, we can divide it up however we want. Which point do we have to use to calculate the height of the rectangle? What point do I have to use to calculate the height of this first rectangle?
Doesn't matter.
It doesn't matter as long as I pick a point between x sub 0 and x sub 1. Could be x sub 0, could be x sub 1. So that's what this c sub k means. C sub k is just some point in the kth interval. And so, if we were to add up all these areas, then that would be the area when we use n of them, the sum when we use n of them, is just equal to the height at some point in the kth interval times the width of the kth interval.
Mm-hmm.
And just add that up for all k of your rectangles. So here's the sum when we let you use pretty much any partition you want, and we let you use any point you want to get the height of the rectangle. Here's how you would represent the sum of n rectangles. And now here exactly is the definition of a definite integral. Definite integral from a to b is the limit as, now, sorry, that's written kind of small. We have 2 bar p 2 bar. This is called the norm of the partition, and it means the biggest gap in your partition, the largest interval. So let me do this very concretely for a second. Let's say I had the partition 0, 0.5, 0.7, 1. Here's a partition from 0 to 1. My biggest gap goes from 0 to 0.5. So the norm on that would have been 0.5. This one goes from 0 to 0.5. This jumps 1/2. This jumps 0.3, or this jumps 0.2, this jumps 0.3.
Yeah, I get
You with me? So that's just notation for the biggest gap in your partition. So what is the definite integral from a to b equal to? It equals to the limit as your norm of your partition goes to 0 of the height at any point in the kth interval times the base of the kth interval. This, what we've been using, is just a special case of that.
Yeah.
We're just using the case where we evenly divide it up. And we're using the right-hand point every time. So here's what it is in general, the definition. This is a special case, and when you have to calculate these things by hand, I almost always use this thing directly. Make sense? Okay, so that was a lot to swallow. That was pretty much throwing 5.3 in there, but we'll cover 5.3 next week.
How does that relate to the antiderivative?
Okay, so 2 last things we want to talk about. I want to do one example from the book and briefly introduce the concept of average height. And then I want you to see how these things relate velocities and distances together, and how they're connected to antiderivatives like you've been saying.
Okay.
So let's first do this one, and then we'll come up and do this one. So actual problem from the book, something like exactly what you're going to be asked to do on your homework. The author says, here we've got the function sine of x on the interval 0 to pi. And it goes up to 1. The sine at pi halves is 1. That's what we're looking at. Now, the author asks you to estimate the area, dividing it up into 8 even rectangles using upper sums. You with me?
Okay.
So we're going to divide this up into 8 even rectangles.
Where did you get 8?
He just gave you, the author gave, it was in the problem.
Okay.
It says, approximate this area using 8 evenly spaced rectangles using an upper sum.
Which means you're overestimating something.
Which means we are going to be overestimating the area. So that is splitting up into 1, 2, 3, 4, not quite, so I need to cut this in half. So what's my x-coordinate here? Just to help me keep track of this. That's 7 pi 8ths, right?
Yeah.
This right here is at 5 pi 8ths.
Mm-hmm.
This right here is at 3 pi 8ths. And then this one right here is at pi 8ths.
Okay.
You with me? So the rectangles we're talking about is this rectangle, this rectangle, this rectangle,
Why
sorry,
don't we just take the limit on this?
this rectangle. No limits. So the first section is just very much by hand, just calculate the area approximation. Nothing fancy. I told you what we did over there is way harder than anything you're going to see in your homework.
Okay.
I wanted you to see where all this was going.
Gotcha.
So we're just calculating the area of those rectangles, and literally that's all we're doing. And we're adding them up. So let's just quickly write out the math. First off, what is the base of each of my rectangles?
Pi 8 plus k.
Pi 8.
Okay.
So we're going to do, my first rectangle is its base times, what's the height here? It's the height of our function at pi 8 times sine of pi 8. You see that? Because this is a sine function.
Oh, duh. Yeah, got you.
Okay, there's the area of our first rectangle. Plus, what's the area of our second rectangle?
Pi force, sine of pi force.
What is the base?
Pi 8.
Pi 8.
Pi
They're
8.
all going to have the same
Yeah,
base.
that's right. And then
Pi 8 times the sine of pi force.
and so forth.
Plus pi 8 times the sine of
pi over 8.
3 pi over, for some reason I heard wrong. Plus, dot, 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 plus, what's our last one going to be?
Pi.
No, notice that we're using the right-hand points for these rectangles, and then the left-hand points for these ones.
Oh.
So it switches, because you're using the upper sums.
Oh, yeah.
Okay, so what is our last rectangle?
7 pi.
What's the base?
It's pi 8.
Pi 8.
Sine of 7 pi over 8.
Oops, 7 pi over 8. And you're literally just going to plug that into your calculator, add it all up, and it's going to spit out a number for you. And so you're going to get that the area is approximately, when you plug all that in, and let's see, just in my head really quick, 2.364, whatever the units were. I didn't really do that in my head. I wrote it right there so I won't forget. Okay, so that is approximately what the area is. If you go plug it into your calculator, add them all up. Sanity check, the area better be less than 3.14, because that would be the area of this whole rectangle, right? From pi to 1, what's 1 times pi? Pi, or roughly 3.14. So, quick sanity check. Better be less than 3.14. Yeah, that seems like a reasonable number for whatever that was. Don't trust the picture too much. Okay, and it also wanted us to approximate the average height. How do you get the average height of a function? Let's not look at it in that special case. Let's do it just slightly more general, and then we'll look at it in that special case. So say I've got some curve here, and I want to know its average height on this interval. So let's pretend that this whole thing is base, and the area of this curve is just A. How do I get its average height, knowing the area and the base?
5 by 2.
The idea is, what is the average height? The idea is, let's create a rectangle that has the exact same area as the curve,
yeah.
and then whatever its height is the average height. So, what is h here? If you know that its area is A and its base is B, what's h?
B.
You know that the area has to be equal to what? How do you get area of... Huh?
BH.
BH.
So H is A divided by B.
Perfect, you see it. So the area has to equal B times H, the H that we're looking for. B times H. So H, in that case, has to be A over B. Or in other words, in general, our definition for average height, is always equal to the area divided by the base.
Yeah.
And that gives you the average height. So now we're supposed to calculate the average height of this thing. What would the average height of this be approximately? Y average. We just take the area, whatever we calculated here,
2, 6.
and divide it by whatever the base is. What's our base?
Height.
The base of the whole thing.
Pi.
Pi. And so our average height, I didn't remember to get this out of the book, but it's going to be something like 0.7, I don't know, 0.716, blah, blah, blah. It's going to be smaller than 1 because we're taking that and dividing it by 3.14. So that's a made up number. Make that very clear. Okay. All right, so last thing now is just trying to connect this with velocities and positions and how you've already been doing antiderivatives.
Time graphs.
Yeah, so let's look at, here is your velocity. Your velocity, you are walking and you are speeding up as you go. And you're running faster and faster the more time passes by. This is tracking your velocity. So right at time 0, your velocity is 2 meters per second. After 1 second, your velocity is 3 meters per second. After 2 seconds, your velocity is 4 meters per second. After 4 seconds, your velocity is 6 meters per second. So you're speeding up as you're running. You with me? Now our question is going to be, from 1 second to 4 seconds, how far did you run?
The area.
Well, let's think, if you were just running, so let's see, after 1 second, how fast are you running?
3 meters a second.
You're running 3 meters per second.
Right.
So if you didn't speed up from when we started our watch, then you would have been 3 meters per second the whole time, and you would have gone, how fast would you have gone from 1 second to 4 seconds
12 meters.
if you stayed just 3 meters per second the whole time?
12 meters.
From 1 to 4. How much time is between 1 and 4?
3 seconds.
3 seconds.
Oh, so like.
So if you had just gone 3 meters per second the whole time, for those 3 seconds, you would have gone 9 meters per second. Or 9 meters, right?
Yeah. Oh.
But you weren't. You were speeding up as you went. Right?
Mm-hmm.
And so you started out with a speed of, well, I'm not sure the best way for you to see this. How's another way we could have said this? What was your average speed the whole time?
3 meters.
So you started out going 3 meters per second. You ended going 6 meters per second. So what was your average speed?
Go over 3 seconds.
Huh?
9 divided by the base is 3, so 3. The average would be 3.
6 plus 3
9.
Divided by 2.
is 9. Divided by 2, because you added 2 numbers together.
So it's 4.5.
Okay.
You're taking the average of 2 numbers.
4.5 meters.
You're
Oh.
ending, yeah, so your average speed is 9/2 meters per second, right? Drawing that as though you were going 9/2 meters per second, let's see, that's the same as 4.5, so we have 3, 4, 4.5. That would have been as though you did this the whole time. You see that? And so that area would have been the exact same as if we took that triangle and flipped it down there.
Which triangle?
If we would have taken this triangle and flipped it and stuck it right there.
Ah, gotcha.
And that's the same as taking your average height times that thing.
Right.
You with me?
Mm-hmm.
And so in either way, you see, what's the total area underneath that curve?
The average plus.
Oh, it's 9 meters.
You can think about it as your average speed times your total time. So multiply it by 3, what do you get?
327 over 2.
27 over 2. That's one way you could have thought about. We could have just calculated this area like the way I was initially doing it, but I felt like I was confusing you guys. We could calculate that as 9, and then what's the area of this piece? What's the area of this rectangle, or triangle?
It's half the base times the height.
Half the base times the height. What's the base? 3. What's the height? 3.
3. So it's 3 halves times 3. So it's
You see how it's just 9/2? Or it's exactly half of the square down there? I don't know how this is easiest for you to see it.
Let's see.
Okay, so 9/2 plus 18/2 is
27.
27/2. So is it appealing to your intuition that that's 27/2?
Yes.
Okay, now we're going to go through not calculating
Wait, is that 27 half meters?
meters. Okay, so now let's get this the antiderivative way.
Okay.
You with me?
Yes.
Okay.
So here's our velocity function. Velocity is a derivative of position. So what is our position function? S of t.
It's,
You just integrate that. What's the integral of 2?
2t.
it's going to be t squared.
Okay, we can start with the t. So t squared
Yeah.
over 2. Add 1 to the exponent and then divide.
Plus.
Oh, that's right.
Plus
Plus
T2.
2t,
2t plus our initial position, some constant c.
which is 2 here.
Right?
Is it 2 in this case?
Yeah.
Or actually, do we know?
No, it's 2 here. Well, in that specific one.
No.
Because of the y-intercept.
No, it's possible. My bad.
Oh, we're talking about position.
We're making this as a function of t.
Yes.
How far have you moved after 0 seconds?
0.
Okay, so we're fine with that so far?
Yeah.
Good? Now, this tells us our position after some amount of time. What was our position after 4 seconds?
12.
16 divided by 2 is 8, plus 8 is 16. What was our position after 1 second?
Um,
2.
1.
What's 1 divided by 2?
half.
A half. Plus 2 is?
1.5.
2.5, which is
How many halves is it?
5 halves.
5 halves, thank you.
Yeah, I
Okay, we good?
Yeah.
So this was your position after 1 second. This was your position after 4 seconds. We want to know how much you went from 1 to 4 seconds.
Displacement.
Yeah, your displacement, so that would have been s at 4 minus s at 1, right? That would tell us how far you went from the 1 second mark to the 4 second mark. And so you get 32 halves minus 5 halves is
It's 27.
27 halves, which is exactly how we calculate that area.
Oh, cool.
So that's exactly what an antiderivative is giving you.
Oh, weird.
I like that a lot.
So let me write this out explicitly what we did. We calculated the integral of our velocity t from time equals 1 to time equals 4 with respect to t. That's what we did. Now here's the trick to solving these. What's the integral of that? We already calculated that. That was 2t plus t squared over 2, right?
Oh, yeah.
And now we need to, the way that we say this is we evaluate this from 1 to 4. In other words, plug in 4 and then subtract what you get when you plug in 1. And that's exactly what it gives you.
Wait, can we graph the position function real quick?
Graph what?
The position function real quick?
The position function?
Yeah, what does it look like?
So the position function over here is going to be, I mean, we just have to like approximate it.
Right.
After 1, we're up here at 5 halves. After 2, it's some sort of parabola.
Uh-huh.
So it's approximately like that. I don't know how much it matters, drawing it out nicely. So just connecting your intuition. Don't worry, we'll learn how to calculate these things later. That's jumping ahead.
Right.
But just connecting your intuition for how integrals are related to antiderivatives. And how calculating this using the area is exactly the same thing as using the antiderivative. They're giving us the same answer.
So we found the difference between two values on the antiderivative gave us the area of the derivative.
We calculated the area. So if we would have used an integral, it would have given us this area,
Yes.
which was the same thing as calculating the antiderivative at the end point minus the start point. The antiderivative basically gives us the area up to that point. So if I take the antiderivative and I plug in 4, that gives me the area up to 4. But we didn't want the area up to 4. We wanted the area up to 4 minus the area up to 1,
Okay.
which gives the area in between.
So if derivatives give you a function that tells you the slope at every point, then the antiderivative gives you a function that tells you the area
From 0 up to that point.
from 0 up to that point.
Yes.
So,
With one gotcha. If it goes under the curve, the area comes out negative. So if you were to calculate the integral of a function that looks like this, from this point to this point, you'd get 0.
right.
So this counts as positive area, this counts as negative area, and they cancel each other out. That's one gotcha. But we'll have more to say about that. Because the height of these rectangles is negative. And so a negative height times a base cancels out a positive height times a base.
Right.
And that's why it comes out that way. Okay, so that was it for that section. And Alex never showed up, that's not good.
No, he